What happens if you try to approach something that's the Planck length? You get so much energy in there. What you do is you form a black hole. And then you put more energy in, you try to see what's going on, and the black hole grows. And so you get to a point, which is around the Planck length in size, where you can't, in principle, try to resolve the structure of this thing. So I think it is legitimate to make the argument that given what we know about the universe, given the measurement we make of the strength of gravity, the measurement we make of Planck's constant, and the measurement we make of the speed of light, then there is something fundamental about this very tiny length, 10 to the minus 35 meters. Of course, the things we can really get a feel for are things that are around, let's say, a few inches, a few centimeters to a few meters. But then when you start to talk about the distance to the planets, or the distance to the sun, the so-called astronomical unit, 93 million miles. What does 93 million miles mean? So look at the moon. The moon is the same radius on the sky as the sun. You know that because of total solar eclipses. It is a coincidence based on the way that our solar system has evolved, but it's a nice coincidence. So we can perhaps conceive of what the sun looks like on the sky. 93 million miles away. You can fit 1 million Earths inside the sun. So how do we conceive of that? The radius is something like 100 times the radius of the Earth. That means that if you got in a passenger aircraft, well, it'd take something like a year to fly around the sun in a passenger aircraft. It becomes inconceivable. And the sun's quite a small star. So then we start to think of bigger distances. So the most distant object that we created, we built, the Voyager 1 spacecraft.
3, 2,